Welcome to the lecture on fundamentals of satellite communication system. My name is Charles. The lecture outline will discuss, among others, the basic concept of satellite communication, the many components of a satellite communication system. Then we'll discuss elements of communication system, including the satellite transponder, types of satellite orbits. Then I'll look at free space path loss, signal propagation, delay, all the way up to the advantages and disadvantages of satellite communication. So let's begin with an introduction. When we talk about satellite communication, this is nothing but a wireless communication system that uses some repeater satellites to relay signals from distant points on Earth. And as you can see from the diagram on the right, you've got two Earth stations, the first and second. And if you are sending information to from the first Earth station to the second Earth station, you will need a satellite to basically relay your signal, act as a repeater. And that is when you have two stations that are separated over a wider distance. So because of that, you can actually see that satellite communication enables long distance communication. It covers large geographical areas, so you're able to send signals over large geographical areas. And that's why it's widely used in television broadcasting, the internet, navigation, weather monitoring, as well as in defense, among others. So next, I want us now to look at the basic concept of a satellite system. Now, a satellite acts as a repeater, like I stated in the introduction. It's a repeater that is located in space. In fact, what we call a satellite is what is actually launched in space. The ground station from source, whether from the source side and the destination side, those are not satellites. They are essentially the transceiver stations that you can use to transmit a signal from source to destination, and you can also use them for receiving the signals, as the case may be. But the actual satellite is essentially what is launched in the space. And if you look at this diagram here, what is the actual satellite is actually this equipment there. And what a satellite does is to receive the signal from the ground station, especially from the source, via some uplink of the signal being essentially uploaded to the Earth satellite. And once the signals are received from the Earth station through the uplink component of the telecommunication system, the signal is then amplified and goes through some processes, right? So once it goes through some more amplification, the noise is filtered out, and again, the signal is further transmitted down using the downlink. So it sends back to another Earth station using the downlink, as you can see here. So that's essentially the concept behind the satellite system. It is essentially there to relay signals from one ground station to another ground station. And these satellites are usually launched in the space where they act as repeaters. The next thing that I want us to discuss is now the components. There are three main components of the entire satellite system. You need to have Earth stations, which will house the transmitter and the receiver. And these Earth stations could be one or two. In most cases, there are two. And then you need also the transponder, which is the second component, the actual satellite, which is launched in the space, which will act as a repeater. And as we know, any repeater is essentially to get the signal, regenerate the signal, remove all the noise, amplify it, and then relay it or send it to the receiving or destination ground station. So then you also need the next components, which are key. Here are the communication links. In this case, you've got the uplink and the downlink. These are very, very important. So 3 components essentially makes up the satellite communication system. You have the earth stations, which could be 2, source and destination. Then you've got the transponder, which is the satellite itself, launched in the air or in space. And then you've got the 2 communication links for uplink and downlink. Let's look at the elements of a satellite communication system now. Again, when we talk of elements, the first element is the earth segment, right? This is where you have the ground-based stations, and it includes antennas, transmitters, receivers. The function of these earth segments are essentially to transmit a signal if using the uplink link, and also to receive the signal during the downlink process. But the earth stations or the ground stations also function in tracking the transponder, which is essentially launched in the space. So the third function is that of tracking the satellite or the transponder. Remember, this is transponder or the actual satellite will be orbiting at a certain angle in the earth. So it has to be tracked also at the signal at every moment. You are able to capture the signal, and then we are able to capture or send the signal as the earth, as the transponder is rotating in the space. Then the second element, which is also very, very important, is the space segment. So the space segment, that's where you have the actual transponder now. You notice that it has to be powered. It has a power system, usually powered from solar. And then it will have antennas also for receiving the signal from the earth station, and the same antenna for transmitting the signal to the destination and ground station. And then you've got also the various controls that are used to essentially ensure that the signal is sent to the correct destination once it is received from another ground station. So that's a transponder. I'll talk about it in detail shortly. But having looked at this now, let's narrow inside the transponder. What is inside the satellite transponder itself? So if you look at this block diagram, what it has is that you have an antenna receiving the signal from the ground station via the uplink process. And once the signal is received, let's assume this signal is 14 gigahertz. It will go through the process of amplification using the low noise amplifier LNA, and then it goes into the down converter. In the down converter, 2 signals are mixed there. There's one from the local oscillator. So in this case, you have the 14 gigahertz coming from the LNA, getting into the down converter, and another one from the local oscillator of 13 gigahertz. What the down converter would do is to basically subtract 14 minus 13, and you have the output signal out of the down converter there of 1 gigahertz as an example. So this 1 gigahertz passes through the band pass filter. So what will come out of here is essentially the 1 gigahertz. And this will also go through some up converter where it mixes with another signal from the local oscillator. In this case, you have 1 gigahertz getting into the up converter, and it mixes with another local oscillator signal of 10 gigahertz. The up converter will essentially add the 2 signals, so that what you have now is 10 plus 1 gigahertz, giving you 11 gigahertz, which is your radio frequency signal, which will pass through the band pass filter, and then this will go further to the power amplifier, and then the 11 gigahertz is transmitted to using the downlink to the ground station where further processes are done. So that's essentially the inside of a transponder. It is just there to capture the signal as it is received from the ground station, regenerate the signal, amplify the signal, pass it through some filtration process. Then once the down conversion process is over, it goes through the up conversion where another local oscillator 2 is added, and then the signal is relayed to its correct destination. So that's about the satellite transponder. Next, I want us to talk about the uplink and downlink. So when we talk about uplink, this is from the Earth or ground station to the satellite, and downlink, it's from the satellite, which is located in space, down to the another ground station on Earth. Usually during uplink, what is key to take note here is that the frequency is much higher for the uplink and much lower for the downlink. If you remember what we had in the previous slide where we're showing the transponder, we had 14 gigahertz, which is much higher than what was actually coming out on the downlink, around 11 gigahertz. So usually the uplink frequency will be higher than the downlink frequency. Then in terms of power as well, the power on the uplink will be higher compared to the to the downlink where you have lower power. So you need to take note of these differences between the uplink and the downlink frequencies. So you cannot have an uplink frequency which is lower than the downlink frequency. It's usually the other way around. The uplink frequency must always be higher than the downlink frequency. Now, next I want to talk about the frequency band of operation in the satellite communication. If your application is in the mobile communication, normally you'll be operating in the range of 1 to 2 gigahertz. If you're operating with weather and radar communication, you need to operate in the 2 to 4 gigahertz. For TV and telephone, you can operate in the C band, which is 4 to 8 gigahertz. And then for military is 8 to 12 gigahertz. And then for DTH TV and high-speed internet, they are operated between in the 12 to 18 gigahertz and 26 to 40 gigahertz respectively, which is essentially the Ku and the Ka band. Okay, next I want us now to discuss the types of satellite. There are various types of satellites. Essentially, there are three that rotate in a circular motion, and the other one, which is the fourth type, which will operate or circulate, which will essentially orbit in an elliptical format. So let's begin with the first type of satellite. We have what is known as a geosatellite. The geosatellite, this is essentially geostation orbit satellite. It's usually launched at an altitude of close to 36,000 kilometers from the center of the Earth. And it's usually launched along the equator. And when you look at it, it would appear as though it is stationary. It appears stationary, but it's actually orbiting around the equator. This type of satellites are mainly used for television broadcasting. Very, very essential for TV broadcasting. And also take note, the altitude, right? The altitude from the center of the Earth, it's around 36 kilometers, 6,000 kilometers. Then you've got also what is known as the LEO, which is low Earth orbit. This one goes between 160 to 2,000 kilometers from the center of the Earth. It is usually used for internet constellation. So you launch a number of these, and normally they are launched near the South and the North Pole. They are usually they have lower delay, but requires many satellites to be launched for you to have continuous internet through a 24 hours cycle. So you need to launch a lot of them. And a good example of LEO satellites is what we Starlink. Starlink, an American firm, has launched a lot of these low Earth orbit satellites, and they are mainly used for internet connectivity. Next, you've got what is known as the medium Earth orbit satellites. This one will be between 2,000 and 36,000 kilometers. So you launch it at a height from the center of the Earth between 2,000 to 35,000. Mainly, most of them are launched at around 10,000 kilometers from the center of the Earth. And these medium Earth orbit are mainly used for navigation systems, and a few can also be used for radar systems. So navigation systems make use of, you normally apply the medium Earth orbit satellites for that application. Then we've got also what is known as the highly elliptical orbit, HALE. HALE is a satellite orbit with a very elongated elliptical shape. And unlike the other three that are circular, this one actually it's elliptic in nature. One end is closer to the Earth, and the end that is closer to the Earth is essentially known as a perigee, and the other end is far from the Earth, which is known as the apogee. So because these satellites are launched mainly closer to the Earth, they are best used in applications in areas that are closer to the to the Arctic and polar areas. That's a coverage area. You normally launch them near the poles, the South Pole and the North Pole. And that is why they are useful for countries that are closer to the South Pole and the North Pole, like Russia, Canada, Northern Europe, and including Southern Africa, which is basically closer to the South Pole, as well as most of these European countries that are closer to the North Pole. So, and you normally, launch the HALE in areas where the geosatellites actually tends to perform poorly. So they are usually used to complement, to cover areas where the geosatellite is unable to cover. And in terms of its application, just like the GEO, they are mainly used for television broadcasting in those areas where they have good coverage. So let's look at the comparison between the three and between the four types of satellites. We've got the LEO, which is usually circular in shape. The coverage is small. It's mainly used for internet and also imaging. So we use it mainly for internet and imaging applications. And then you've got the MEO, which is also circular, medium area, mainly used for navigation. The GEO, mainly used for television broadcasting. It covers, it has a fixed large area of coverage, but there are areas where it cannot cover. Therefore, we employ the elliptical Earth orbit type of satellite, which focuses mainly at the North Pole and the South Pole, and it's used mainly for polar communication, but you can also use a bit of it for television broadcasting to complement GEO. Next, let's talk about a few calculations that we can need to do under satellite communication. We have got free space path loss, which can be calculated given the transmitted power, gain at the transmitter, given also the gain at the receiver. You can calculate what is known as received power, either at the transponder, right, or at any of those transmitting Earth stations. You can actually calculate the received power using this equation. And this is equation we actually discussed when we were discussing antennas as well. And you can also calculate, right, what is known as a free space loss in decibels, given the distance between the center of the Earth and where that satellite is. And also if I know the frequency, the uplink, normally this is the uplink frequency. If I know that frequency, I can calculate the path loss, right? Equally, if I know the distance from the transponder to the ground station, right? So the received power at the ground station can be calculated if I know the downlink frequency F and the distance from the corresponder to the earth station. So that's essentially the equation to calculate free space loss, path loss, which is essentially 20 log 10 D, where D is the distance in kilometers. Please take note, D must be in kilometers and F must be in megahertz and not in hertz or gigahertz. So if F is given in gigahertz, you have to convert that into megahertz. If it is given in hertz, it has been converted into megahertz before you can plug it in the free space path loss equation. Next is the calculation. Now here what I've done in the next slide is to give an example. Suppose we are given the distance from the center of the earth to where the transponder is as 36,000 kilometers. And this is the case for geosatellite. And the frequency at which you are actually, the uplink frequency is 6 gigahertz, which then if you remember, you have to convert that into 600 into megahertz, which will be 6,000 megahertz. Therefore, the free space path loss can be calculated from 20 log at 6,000 kilometers plus 20 log 6,000 megahertz plus 32.44, which gives you 199.12 decibels. So that's basically an example to illustrate free space path loss calculations. Next, I want us to now talk about still under free space path loss. We can also calculate the power density of a signal. If I know the transmitted power, I also know the distance. So transmitted power will be 4 pi d squared. You can also actually calculate it as transmitted power divided by 4 pi d squared, where 4 pi d squared is the area of a sphere under which the signal is traveling as it moves in the space. You can then also now calculate what is known as a propagation delay, which is given by d over c, where c is the speed of light and is 3 times 10 to the power 8 meters per second. And that d is normally known as a round the distance it takes to move from the ground station to the transponder and from the transponder to the earth station. So that is also known as the round trip distance. So D is essentially your round trip distance, and the round trip is essentially the distance from the ground station to the transponder and from the transponder or the space satellite to the ground station. So that gives you D, which is a round trip distance. So if I know the height of the satellite, for example, we know that from the center of the Earth of a geosatellite, in the center of the Earth to the where you launch the geosatellite, 36,000 kilometers, the round trip will be double that distance, which is essentially 72,000 kilometers. So that 72,000 kilometers becomes your D, or round trip distance, divided by the speed of light gives you the delay. And in this case, it will be 0.24 seconds. You can do the same for a MEO, for a LEO, which is normally around 1,000 to 2,000 kilometers, or the MEO, which is around 10,000 kilometers from the center of the Earth. You can as well calculate the delay. And obviously, this delay is less for LEO compared to GEO type of satellite. Next, we can also calculate what is known as the antenna again, either the ground station, the transponder, or even the ground station from the source. The transponder, which is a space satellite, can also calculate the gain of those antennas for the receiving station, which is another ground station. So if I know the area, so it will be just 4 pi A divided by wavelength squared. And then you can convert that G into decibels by multiplying 10 log G. So that gives you the gain in decibels. But if I know, for example, the diameter of a dish, D, I can also calculate gain given the efficiency as efficiency multiplied by pi D over wavelength squared, where the capital D there now denotes the diameter of a dish that is used to basically either transmit or receive the signals. And giving an example here, let's suppose we have a dish diameter of 2 meters, the frequency of operation is 4 gigahertz, and the efficiency is 60% to 0.6. You can therefore calculate your, first of all, the wavelength, which is essentially the speed of light divided by the frequency, which is 4 gigahertz, and you get 0.075 meters as your wavelength. Then for the gain, it will be efficiency multiplied by pi d over the wavelength, everything squared, and you get 4210 or 4,210 as a gain. Then you can express this now in decibel by simply multiplying 10 log 4210, which gives you 32.2 decibels. So what are the advantages and disadvantages of satellite? Number one, when you talk of advantages, satellite communication offers wider coverage. You can have a global communication by just planting a number of satellites, and then you have a number of satellites in the space, and these are communicating with a number of stations here on Earth. So it offers wide coverage. Number two, it supports remote and rural areas. You're able to cover rural areas well, where you can't run cables. Therefore, satellite offers that advantage. And also it's reliable for broadcasting. So when you talk of television broadcasting, like we saw in the GEO, these satellites offers good signals for broadcasting. It also allows for quicker deployment, though of course that comes at a cost, but can you quickly deploy solutions for internet streaming, TV broadcasting, weather navigation, imaging, checking of minerals, and so on and so forth within a shortest period of time by making use of already launched satellites. So those are some of the advantages. But there are also disadvantages. The initial cost to launch this satellite is very high. Remember, there is that calculation we did for signal propagation delay. So there's always that delay, especially for GEO. Satellites are also affected by interference, especially in the rain season. You find that the signal quality tends to be poor. So signals are affected by atmospheric interferences, including rain. There is also limited bandwidth for some platforms. So you can't operate them over very wide bandwidth. So this marks the end. I've also given some tutorials for you to try. I hope you enjoy the presentation.